We turn our attention to lenses. We're going to talk about the two different kinds of lenses, the lens equation, and how these all work together. Lenses work on the principle of Snell's law, where light will bend when it goes through a material like glass. And so here's a picture of how a converging lens works. So a converging lens takes the light ray. Now if you draw this line, now this line is that line we've always been interested in, which is the normal to the surface. Now because this lens is curvy, this points in a weird direction, but if you look right where it's hitting the surface, it's at 90 degrees to the surface. And so the light will be bent a little bit, just like we expect. And then when it hits the second surface, the same thing will happen. Again, we draw that little normal line. And then what ends up happening is the light is focused on this point over here. And so this is how, in general, this case, the converging lens works. The diverging lens will work similarly. It's just that it'll make the light rays diverge instead of converge. And so all rays parallel to the principal axis will pass through this point that we call the focal point. And so we're going to find a lot of similarities between mirrors and lenses. Mostly similarities, a few differences, and so we'll try to highlight those. But if you are doing pretty well with mirrors, you should do pretty well, or at least pick this up pretty quick, I think. So let's look at converging lens and the principal rays that we draw. And so these are very similar to the rays we would draw with the mirrors in order to get our pictures. So the first ray is a ray parallel to the principal axis, passes through the focal point. And so this works just like we were just thinking about, we were just drawing a little bit ago for the converging lens. And so this principal ray parallel to the axis passes through the focal point. A ray through the center of the lens is not refracted at all. And so this line goes straight through the center of the lens and it keeps on going. And just like with mirrors, all we really need is two of these lines to find our image. But it's kind of nice to have a third one just to make sure we didn't make a mistake. And so the third one is rays through the focal point emerge parallel to the principal axis. And so if I draw this ray through the focal point, when it hits the lens, over here, it'll head off parallel to the principal axis. So again, these light rays are all leaving the tip of our arrow, which is our object. And so when they meet over here, that'll be the tip of the image. And so here's the image. And in this case, the image is real, meaning the light rays really do interact there. It's inverted, it's upside down, and it's enlarged, it's bigger. And so this works very similar to how we would look at the image for a mirror. Now, if you're like me, this page will be very important because I think you'll find that doing some of the actual calculations for this stuff isn't that hard. But sometimes, for me, connecting it to the real world can be a little bit tricky. And so here's just a couple pictures showing how these lenses could be used in the real world. And so here, this top one is what lens would look like for a camera, perhaps. And so here we have our object. Our object is sort of a far distance away. It's further than twice times the focal length away from the lens. And what you do is you have a really tiny image, and it's upside down. So if you ever looked at the innards of a camera, the image comes in upside down, similar to how our eye works. And it's a smaller image, and so you would project this image, it's a real image, on the back screen of your camera. And so it's a real image, the light rays really hit there, and it'll be nice and focused, and that's what would make the picture in your camera. And we'll do some stuff in practicals sort of working like this. Here's how, say, the projector in Con Hall might work. Okay, so there's a lens here, and so this is the object, which would be the slide that we're looking at on the projector, and so you would shoot light through it. And then you project it, a real image, much bigger than the actual size of the slide, some far distance away. Again, it's upside down, so the projector accounts for that. Inside the projector, the object would actually be inverted so that we all see everything right side up. And finally, this is how you might draw the ray diagram for a magnifying glass. And so here's your magnifying glass, and maybe your little handle would be right over here. And you'd be looking at some small object, and what it does is it makes a virtual image. The light rays really don't come from there, they just appear to, and that image seems much bigger than whatever you're looking for. So again, look these over, because I think it is important to sort of connect what we're doing to things that actually work in the real world. Now our next lens is a diverging lens. So this one works sort of as an opposite principle. The converging converges the light rays. This diverges the light rays. And so we're going to have three, rays to draw to help us find our image when we're actually drawing this. And here's the three rays. So a ray parallel to the principal axis will shoot out as if it was shot through the focal point. And we'll show you in a second what we mean by that. Rays through the center of the lens are not refracted. That's just the same as with converging. And then rays towards the focal point emerge parallel to the principal axis. And so that's really important. I think the diverging is a little bit harder to draw than the other ones. And so this ray here, if you looked at it, was intended to go through this focal point over here. I'm sorry, I can't really draw this very well, a straight line there, but it's intended to go through that focal point. And so that ray going through the other focal point will come off going straight. And now let's backtrack these lines. And so again, this one here, our very first one, so it was a ray parallel to the principal axis, shoots off as if it went through the focal point. Well, this is this backtracking it over here to the back focal point. So it's a little bit hard to kind of see how to draw that one. Definitely harder. In this case here, your image is right here. This is where the three rays come together. Again, we only need two, but it's nice to have a third. This image is virtual. The light really doesn't come together there. You have to backtrack it to get it there. It's upright and it's reduced. And just like with mirrors, we have a lens equation, and it's the same equation. Okay, so it works very, very similarly. There's just a little tiny bit of differences. So d0 again is our distance to the object from the lens, and so we say it's positive if in front, negative if behind. di is the distance to the image from the lens, positive if behind, and then negative in front. So again, we're sort of saying that this is the front over here, and this is the behind. So this is where it gets sort of different. So we have a front and a behind, and so you expect, or at least if the object is positive, then it's in front of the lens. If the object is negative, it's behind the lens. We'll talk about what a negative that could be. Usually that would intend some other optical device, like another lens or something. di, the distance image from the lens, is positive if behind, negative if in front. So we expect the image to be over here. So it's positive if it's over here, and then it'll be negative if it's on the other side of the lens. And then the focal length is positive if converging, negative if diverging. And we have the same equation, and so for this sort of example here, like in this picture, you can imagine that if this is DO is 15 centimeters and the focal length is 10, which sort of adds up to what we have over here. My DI is 30 and it's positive, and so the image comes out over here. And the same thing with our magnification, works just like with the mirror, and so here the magnification is -2, so it's about twice as big roughly. Remember that the magnification, another way to write that is HI over HO. And I think the big difference here is just that how you do the image. So with the mirrors, the image is in front because it's reflected off, and so if it's a real image, it's going to be in front of the mirror. But here, since the light's passing through, it's a real image if it's behind. And so you got to be careful with that. Let's try a few examples dealing with lenses. So here we have a clicker question: where should you place an object so that the image is real for a diverging lens? So think about this, maybe pause for a second and we'll talk about it. All right, so similar to a mirror, this diverging lens cannot create a real image. So this is the same thing for a convex mirror, if you remember. And so if we take our equation here, so 1 plus DO plus 1 over DI equals 1 over F. So the thing for a diverging lens is that the F is negative. And so if I solve for 1 over DI, I get 1 over F, which has to be a negative number, and then minus 1 over DO. And so if I have a real image that I'm putting somewhere, a real object, so this is going to be positive. So this overall, this little feature here will be negative. And so a negative minus a negative, and so it will end up being a negative. So a diverging lens cannot create a real image with a real object like this. Okay, so here's an old test question. A ladybug of height 5 centimeters is placed 5 centimeters away from a converging lens. The focal distance of the lens is 12 centimeters. At what distance from the ladybug will its image appear? So maybe this one might take a little bit more time, so pause this one and try working through it, and then I'll go through and give you my solution. All right, when I did this, I got the answer to be B. And so let's go through here and look at this. So a ladybug of height 5 centimeters, we don't really need that. What we really need here is just this information. So 5 centimeters is what they say is how far away the bug is from the lens, and that's going to be the distance to the object. And so we take our equation, 1 over do plus 1 over di equals 1 over f. And we're looking to try to find the di, the distance to the image. So it's 1 over f minus 1 over do. And so for us, we're going to have 1 over 12 minus 1 over 5. And so when I did this and I plugged in everything, I got my di to be negative 8.57. And of course, the units, which I dropped over here for this, would be centimeters. So again, since we're using this all in centimeters, it's just fine to keep everything in centimeters because it's the only thing you're using. So now we got to interpret that. Well, so that's the distance to the image, and what that means for a lens is that this thing is going to be backwards or in front of the lens. Okay, so this is going to be a virtual image. We know that right away. And so this is our di. And so the question asked, at what distance from the ladybug will its image appear? And well, basically it should be back this way, so it'll be the difference between the di and the 5 centimeters. And so if you subtract those, so if you call this, distance x, x should just be the difference between 8.57 minus 5, and so this is sort of like an absolute value. And so when I do this, I get about 3.5 centimeters, and then of course in this case it would be, just like we said, to the left of the ladybug. And so the first part is sort of calculating this, and then the second part is interpreting it, which is oftentimes the harder part. And following up with this same question now, so the ladybug of height 5 centimeters is placed 5 centimeters away from a converging lens. So the same sort of idea as before, and this time the focal distance, the focal distance is still 12 centimeters. So nothing has changed. We're just following up now. What will be the height of the image of the ladybug? So go ahead and pause and try this, and I'll show you my solution. All right, so hopefully you got the same thing I got, which was C when I did this here. And so let's go through and work on this. So we can get the magnification because we know negative di over do. And so the di in this case, so it's going to be negative 8.57 centimeters. And that's going to be divided by the do, which is 5 centimeters. And so the negatives cancel, and I got positive 1.71. And so what we can do then is just say that magnification, another way to write that, is hi over ho. And so we're trying to find the height of the image. So hi will equal m times ho, and so I just put in 1.71, and then we're told that the height of the ladybug is 0.5 centimeters, so 0.5 centimeters, and of course if I plug that in, I get my 8.6 centimeters. And also the other thing is, we know because it's a positive magnification, this is going to be an upright image. So it's upright and it's enlarged, it's bigger, and it's virtual because it's in front of the lens and the light rays don't really meet there.